welcome to our next topic in the electrical machines 1 lectures, and we will start discussing about DC machines. And DC machines and these are rotating machines, rotating machines. Machines I will often write like this. Now, before I start discussing with DC machines rotating, we try to understand how DC voltage can be generated. For example, after the discovery of Faraday's in 1830s or so somewhere, which says that voltage induced in a coil is N d phi dt, and if the coil is moved in a magnetic field which sinusoidally varies, then there will be induced voltage which will be also alternating in nature. This was quite obvious, but nonetheless people started developing DC machines first. And we will see that it is not so easy, because inherent voltage induced in a coil when it is rotated in a magnetic field will be essentially alternating in nature. So, you have to do something extra to convert that AC voltage to DC. If this problem has been brought today, that okay, you want to generate DC, one solution perhaps many people will give that okay, generate AC, because AC generation is so simple, and connected rectifier, get DC over. But in those days rectifiers were also not there at that time. So, it was DC machine. People started thinking that okay, large power I have to somehow. Before that, of course, people knew about batteries, DC voltages only we were used to at very small level of power. Batteries were there, 1.5 volt, connect them in series, get some voltage like that. But large voltages delivering large current, hundreds of voltages, that was not there. Then DC machines in any case was developed. So, to understand the basics of DC machine, we start with this discussion. You imagine that I have a coil, a conductor, this is a conductor, okay? And suppose these two red lines are rails, okay. This is a conductor and these two are rails, it has wheels and it is putting. So, that this conductor can move this way, that way, these are rails. Okay. And let us imagine on the top of this arrangement, I have put a north magnet all along this line, length of the rails, and below this I have put a south pole magnet all along the track. That is, from in the rooftop, if it is on the plane of my table, on the rooftop there is a north pole, and on the floor there is a south pole, in between it is there on the table top, and this table runs infinitely. Now, if that be the case, then the direction of B I must show cross from top to bottom. So, it will be say cross B. Okay. So, B direction, and it is all along this whole length and also along the breadth everywhere it is B flux density, you know. So, this is the flux density B from top to bottom, and this is a conductor. Now, let us imagine that this conductor is moving with a velocity say v meter per second. This conductor is moving with a velocity v meter per second from left to right. And let us imagine, let us assume that, not imagine, let us assume that no friction on the track, no friction on the track and also air resistance, no friction on the track. Therefore, to move this conductor at a constant velocity v meter per second on a frictionless track, no air friction also, you require no force. Therefore, external force acting on the conductor will be 0. That is what Newton's told us. To move a thing in a frictionless environment at a constant velocity, you do not require any force. If no force is acting on any body, then either it is at rest or it is moving at a constant velocity. That is what we know. So, anyway, so to move the conductor at a constant velocity v meter per second, I do not require any external force to be acting. It will go on moving under these assumptions. Okay, that is fine. And suppose this side of the conductor I name it as A, and this side I name it as B, small b, the two ends of the conductor. As the conductor moves, there is a B, there is a velocity, these are at right angles. So, I can apply right hand rule like this here, they will be showing this. So, you see there is a B here into the paper. So, forefinger is B, there is a velocity, thumb gives you velocity, and this one middle finger, the end of the middle finger will give you the polarity of the induced voltage, that is A will be plus, B will be minus, and magnitude of the induced voltage will be BLV. That is this is equal to potential of A with respect to B, that is how we write. A will be positive, BLV. So, and what is L? L is equal to length AB is equal to length, conductor length. So, this much induced voltage will be there, and it will, as it moves with a constant velocity, therefore, this conductor becomes a seat of EMF. So, I can say this conductor is like a battery here, A, B, and its magnitude of this battery voltage is like this. It will be DC, because always the magnetic field is into the paper, I have never changed it, and nothing will happen. Although across the rail, if you connect a voltmeter, it will read BLV, because it makes contact with these are also conducting rails, conducting material, is not, although no current can flow. Now, what I will do? I will connect between the rails a switch and a load, got the point. So, if you wish, if you close this switch, this voltage which is a battery, across it a resistance will be connected, is not, and we expect a current will flow like this if the switch is closed. current path will be, this is the source, it will go and come back. Let the initial velocity be v naught, it was moving with a velocity v naught, say meter per second. Okay. And my target is to find out, okay, when I close this switch, how much will be the current and how long will the current flow, things like that. Now, look here, the moment this conductor delivers power, current here, current will also flow through this conductor, same current, series. Now, we know that a current carrying conductor placed in a magnetic field will experience a force, and what is the magnitude of the force? BIL. Where is B? And you have to apply left hand rule. B is here, I is this finger I, and thumb will give you the direction of the force. So, BIL, this much force will act in this direction, opposite to the direction of motion. The moment you close the, henceforth, so long when the switch was opened, as I told you, conductor was not experiencing any force whatsoever. It was just moving with constant velocity as per Newton's law. But the moment you close the switch, although friction etc. is not there, I immediately find that, oh, it will now experience a force in the opposite direction, is not. Therefore, this conductor AB is acted on by a force. If it is acted on by a force from right to left and it had an initial velocity of v naught, what do I expect? Conductor to decelerate, because no other force is there, velocity will go on decreasing. But if velocity goes on decreasing, this voltage will go on decreasing, this current I will also go on decreasing. Physically, I am first telling. And so, in this way, although there will be this resistance will be heated up, current is flowing I square R T, but can this, how long it will sustain? It looks like that as time passes, after you have closed the switch at t equal to 0, suppose, as time passes, the magnitude of the current will decrease, magnitude of the induced voltage decrease, velocity decreases, and a time will come when velocity will become 0 and all this game will be over, everything will be dead. I mean, there will be no velocity of the conductor and things like that. Now, what I am trying to tell, that when a conductor had a initial velocity v naught and without anybody assisting its motion, and it is also not needed when the switch is open. See, there was kinetic energy stored in the conductor, half m v naught square, is not, when the switch was opened. That kinetic energy was somehow imparted. But when you close the switch, the energy is getting extracted from its kinetic energy, is dissipating here, and that kinetic energy was finite. Therefore, finally, it will become 0, all the energy will be dissipated here. So, this example, if I mathematically analyze, will enhance our this physical understanding in a much better way. For example, for physical reasons I know velocity will become a function of time, the induced voltage EAB will become a function of time and so on. So, I must write down these two equations, equation of motion for the conductor AB What will be the equation of motion? Suppose m is the mass. So, m dv dt, its velocity is always from left to right, must be equal to the force acting from left to right. From left to right, what is the force acting? When the switch has been closed, is minus BIL. BIL is acting in the opposite direction. This is the equation. So, it is a first order differential equation. Now, the question is, what is I? I, a very simple circuit, BLV over R, where R is the resistance. So, I put that. So, minus B L and then I is BLV by R, is not. So, that it will become equal to B square L square by R into V, negative sign, or I can write m dv dt plus of B square L square by R into V is equal to 0, and then divide both sides by m. So, that this equation will become, this m will come simply here. This is the equation. Which is a first order constant coefficient differential equation, and I want to know what is velocity. So, velocity, the solution of this equation is well known. Characteristic root of this equation is minus B square L square by m r. So, it will be some constant A into e to the power minus B square L square by m r into t, is not, and there is no forcing function on the right hand side. So, that is the solution, this is the solution, and I have to determine this A from boundary condition. See, velocity of a mass cannot change instantaneously. When the switch was opened, its velocity was V naught. At t equal to 0 plus, after you have closed the switch, velocity will be still V 0 because of its inertia. Therefore, at t equal to 0 plus, V is equal to V 0 only. So, this gives you A is equal to V 0. What is V 0? The velocity of the conductor when S was open. Therefore, finally, what I get is this, that velocity of the conductor at any time t is V 0 into e to the power minus, and you see it is equal to minus B square L square by m r, that is minus B square L square by m r into t. This is the thing, and velocity will exponentially decay down to 0 as we were reasoning it physically. So, that is expression. Then what is the expression? How current will change? I t is also very simple, because it is equal to B L V by R. At any time current is this. So, I will put it here. So, it will be B L by R, then for V this one, that is V naught into e to the power minus of B square L square by m r into t. This will be the thing, is not? Correct. So this is the, it is coming correctly dimensionally. BLV is voltage by R. So this is the expression of the current. So, both voltage and current, if you sketch, will decay down to 0. This was velocity of the conductor, this is time, and this is the current. So, current in the circuit at t equal to 0, when you close the switch, this is coming correctly, that is V, this current value is VLV V naught by R, then it also exponentially decay down to 0. This is time axis. So, this generator will not last long, okay. But we have understood several things. One is a conductor moving in a magnetic field, it produces a unidirectional voltage, provided everything is north on the top, everything is below is south pole, then when it moves, that voltage magnitude of course becomes a function of time. Now, naturally the question is, if I want to make a sustainable generator, not that after some time everything will vanish, what should I do? That means, I want to get a constant voltage here with some load being supplied, that switch is closed, and at that time I must maintain the velocity. See, if I say that my velocity will remain V naught with this switch closed, then I must demand that there will be an opposing force coming in. You must apply another force from left to right to compensate for that opposing force. So, that once again net force will be 0 and it will run at a constant velocity. Got the idea? That is, you must have a prime mover which will push this conductor hard. The moment you want to extract power out of, because of its kinetic energy only it was delivering power, but now the moment you demand that I want to get power in this resistance continuously, then rather make the velocity constant by compensating this opposing force from left to right, then nothing will be coming out from the kinetic energy to here. Whoever is pushing that conductor at that force which is equal to BIL, it will do that work idea. So, in general there must be a this thing external agency which will pushing it from left to right, that is called prime mover. Okay. So, this is a simple generator without any prime mover. In general, therefore, to make the generator work, there must be a prime mover as I told, and the equation of motion I will write next class. But before that, let me in the same arrangement, let me just study another thing. This was my del. Suppose this was the del, okay, and you know this was my conductor. Okay. And suppose this time what I decide is that this conductor on the rails was resting of length L. Now, what I will do, it was at rest, AB initially at rest, Now, what I do, I connect a battery here through the rails with a switch. So, when the switch is open, nothing happens, it remains stationary, and there is of course, B as usual, I am just drawing two lines, but it is otherwise invading all the areas between the delts B, flux density. If you now close the switch and the conductor was stationary, its velocity cannot change instantaneously, at least at t equal to 0 you close, and I am pretty sure that I 0 plus will be equal to this battery voltage is suppose E by R, it has to be, because at t equal to 0 plus B is still 0, conductor was not moving at t equal to 0 plus, because it has got mass, its velocity cannot change. So, at t equal to 0 plus current will be like this, and what will be the direction of the current? It will be like this I and I. So, I at 0 plus is the moment this is current and it is placed in a magnetic field, it will experience a force which I can get from left hand rule, that is this is B and this is I. Hello, দেখাচ্ছে হ্যালো, এইটা একটু করো, আমি একটু হাতে দেখাবো। আচ্ছা, এটাকে ডট করে দিলে ওইদিকে যাবে না? হ্যাঁ, ঠিক আছে। So, you see this is B, this is I, it is correct. So, this is B, this is direction of I. So, thumb will give you direction of velocity, force. This is called electromagnetic force experienced by the conductor, and the conductor in absence of any frictional force will try to accelerate. Its velocity will now start increasing. Earlier it was 0, at t equal to 0 you have closed the switch, then from t equal to 0 onwards the conductor will start moving, and the direction of the force is from left to right. So, for t greater than 0, conductor experiences, conductor AB experiences a force from left to right, from left to right. And what is the value of the force? BIL, what else? Therefore, things starts moving. I can write down the dynamic equation. What will be the dynamic equation? M dV dt is equal to the force from left to right. I will, velocity is this way increasing. So, this must be equal to BIL, no negative side this time, because this is accelerating it. Okay. BIL. So, this is one equation. What is our target? What is the velocity as a function of time is what, and I as a function of time is what. Now, this is one equation. So, I must have two equations to get V and I. What will be the next equation? Next equation is what will be the expression of I. Expression of I at any time t. See, the moment this happens, it starts moving. We have just discussed a conductor moving in a magnetic field will have a induced voltage BLV. So, for this conductor moving from left to right with velocity v meter per second must have a induced velocity, and what will be the polarity of this induced velocity? This is what we have seen, B, V and L. Therefore, this whole circuit will now be equal to a induced voltage here between A and B, that is BLV, and this thing, your switch here, and please I will connect also a resistance here, otherwise there will be short circuit. Suppose with a resistance this source is, or suppose this resistance is the resistance of the conductor, either way. So there is a resistance here and there is your battery voltage E, and current direction is this. Therefore, I must say that current is E, battery voltage, minus this BLV divided by R. So, I have got two equations. If you want to find out V, eliminate I from this, put it here, you will get one first order differential equation, solve for V, then use the other equation to get the current, and this will continue in the next class. Thank you.